Sir, good afternoon, sir. Shall we wait for 2 minutes, sir?
Yes, yes.
Okay, sir. Thank you, sir. Thank you.
Good afternoon, sir. Shall we start now, sir?
Hello. Hello. Hello.
Very good afternoon to one and all. On behalf of management, principal, staff, and the supporting staff of Mohammed Sadr KJ College of Engineering, I would like to welcome all the participants from various institutions, researchers, research organizations for this 5-day online faculty development program on recent advances and application in chemical sciences. In this 4th day, we have Dr. P. Shanmugam, Chief Scientist and Professor of Chemistry, Organic and Bioorganic Chemistry Division, CLRI, Chennai, have joined with us to deliver lecture on synthesis of functionalized arene for heterocycles. On behalf of Chemistry Department, I would like to welcome Dr. P. Shanmugam sir for this session. And I request all the participants to stay back till the end of the session. And if you have any clarification, kindly come back and interact with our resource person. And I would like to extend our welcome to all the people who are present in this virtual room once again. And I expect your cooperation to till tomorrow, 5th day of this 5-day online FDP program. Now I give the session to the Dr. Devi Bala, Assistant Professor, Department of Chemistry, Mohammad Sadak, College of Engineering, to give the brief introduction about our resource person for the day. Over to you, ma'am.
Thank you, ma'am. First of all, I would like to welcome everyone present in the meeting. Welcome, sir. I'm very much delighted and privileged to introduce our chief guest today, Dr. P. Shanmugam, Chief Scientist, CLRI, Chennai. On the 4th day of online FDP on recent advances and applications in chemistry, he received his doctoral degree from University of Madras, and he has done his postdoctoral research from Princeton University, a prestigious university from US, and Hokkaido University, Japan. He worked as scientist in CSIR NIST, Trivandrum. Later on, he moved to CSIR CLRI, Adayar, Chennai. Totally, he has 30 years of working experience as scientist in the field of synthetic organic chemistry, and he has more than 100 publications with 1,500 citations. He got around 2 crore of research funding for his research work from various funding agencies. He has many awards and grants. One among them is JSPS Fellowship, a prestigious fellowship by Japan government, and he has Boy Scout Fellowship awarded by DST. Around 70 students got PhD under his guidance, and 3 are currently working. He is a national body, life member of CRSI, and life member of Indian Chemical Society, life member of Society of Biological Chemists. And he is a member and board of studies in various institutions and college. With this short note, I welcome our chief guest to present his research work. Welcome you, sir.
So listening. Hello, I am audible.
Yes, sir. Hi.
So, my screen is visible.
Yes, sir. Your screen is visible.
Yes, thank you. So, good afternoon. I think I know many participants personally known to me when I read through the names. Before going to today's lecture, at the outset, I would like to thank Dr. Balakrishnan, who has invited me to give this lecture on the 5-day program. And I should also thank the authorities of the engineering college and also staff member of Department of Chemistry of the college for inviting me to give this lecture. I know how difficult to deliver a lecture immediately after lunch. Everybody is joining late after having lunch, I believe. And I will not bore you much. Usually, organic chemistry is boring or a little bit tired after listening lecture immediately after lunch. Let me try to avoid such boring by giving the research findings of our laboratory on a particular topic, benzene, which is rarely used in organic synthesis as a reactive intermediate. So today's topic starts with the chemistry of arenes. Arenes is a general phenomena, and benzenes are well known to us because benzene has a triple bond in its structure, benzene, and any triple bond in the aromatic system generally we call it as arene. Using this reactive intermediate, our group has been using for the synthesis of functionalized heterocycle, and that is the topic of today's lecture. I will detail you in a little later. Before going to that real topic, I just want to introduce what are all the areas of the research we are doing in PLRI. And even before, when I joined as a scientist at RRL Trivandrum, now it is NIST Trivandrum. It is to brief the how a research group in synthetic organic chemistry has been performing for past almost 25 years or so. So first 10 slides, I just want to give a glimpses of the research output, what my group and my students have been done for the past 25 years. So actually, I started my career as independent scientist, not following my PhD work, not following my postdoctoral work, but by simply reading a literature, a simple name reaction reported by Professor Basavaya and Baylis and Hillman from German, and Morita from Japan. These three people were pioneers in the name reaction, Morita, Baylis, and reaction. And in India, Professor Basavaya from University of Hyderabad has done a tremendous work on this field. And after reading his paper, I was motivated and I followed the name reaction. Not the work what has already been done, but I have used the reaction for the different purpose, with different molecule for the synthesis of variety of heterocyclic compound. I will show you one by one the results. I think many professors, research scholars, and students are there. For the benefit of students, I just want to introduce what is the name reaction, Morita Baylis reaction initially. So a lot of reactions, lot of review articles are there. Now, if you see, if you type SciFinder Morita Baylis reaction, you will get more than 4,000 papers will come. And at least from my group, I have contributed around 60 to 70 paper out of that. So let me introduce what is Morita Baylis reaction. So if you see, I think you can see the cursor and audible also. If any disturbance is there, please let me know when I am giving talk. So if you take any aldehyde, simple aldehyde, benzaldehyde or ketone, acetophenone, benzophenone or something like that. If you take any electrophile that is otherwise called aldehyde or ketone, and if you treat with a double bond attached to electron withdrawing group, that we call it as activated alkene, because if you attach electron withdrawing group to the double bond, this double bond is very active. So generally we call it as activated alkene. So take an electrophile, react with the activated alkene in presence of a catalyst. Usually a catalyst must be an amine catalyst, and you will get a product which is, there is no byproduct, and all the starting material are intact in the product. And if you see the total molecule, it is an atom economic, no byproduct. And more than that, if you see, this product has a double bond, electron withdrawing group, alcohol. You have a lot of functional group in a product. So that is actually very important for an organic chemist to modify further synthetically modification. You can do it. So this is the Morita Baylis reaction, this reaction. So for summarize, take any electrophile, treat with an activated alkene in presence of amine, you will get a product which is called adduct. So Baylis adduct. The reaction is called Morita Baylis reaction. So no byproduct, atom economic, highly functionalized, are the advantage of the product. Coming back to the left side, in the place of X, if you keep oxygen, that is aldehyde or ketone. You can also keep NH. If you keep instead of X is equal to NH, then this becomes imine. The same reaction with imine can also occur, and you will get, instead of alcohol analog, you will get amine analog, that is otherwise called Baylis reaction. So there are several kinds of reactions are there now, advancement. Asymmetric Baylis reaction, solvent-free Baylis reaction, solvated Baylis reactions are there. But these two reactions are very important for the synthetic transformation. So one may ask, what are all the electrophiles one can use? You can see a number of electrons. It is not restricted this, but you can take any aldehyde, fluorinated, ester, isotene, this bridged compound, camphor, ninhydrin, many molecules you can choose electrophile. You can also use any other electrophile. And in place of oxygen, you can also think of keeping nitrogen also, because aza can also be happen. And you can select activated alkene, several activated alkene, acrylonitrile, amide, sulfonamide, alkyne attached compound, phosphorus attached compound, nitrogen attached activated alkene. So you have n number of chances of activated alkene also. And what are all the bases? I said the catalyst. You can use amine catalyst, triethylamine, or this bridged cation amines. And also you can use non-amine catalyst also, titanium tetrachloride, triaryl phosphine, methoxide. These kind of compounds can also be used as a catalyst. So why I am showing this slide is, if anyone is interested selecting a new electrophile, that will be a new addition. Anyone, if you are thinking a new activated alkene, that will be a new reaction. Anyone, if you are achieving the reaction by using new base catalyst, also a new. So think, use your fundamental chemistry, read lot of Bayesian papers, and see whether you can use something new for your future work. It may be a research work leading to a PhD or a manuscript publication. So this is the basic background about the Bayesian reaction, and it's analogous aza-Bayesian reaction. So if you come to my group, first time whatever we are using. So first time we have used pyridine 2-aldehyde, 3-aldehyde, 4-aldehyde as electrophile, N-methyl-lysatine, ninhydrin, ferrocin monoaldehyde, ferrocin dialdehyde, bipyridine aldehyde, biphenyl aldehyde, monoaldehyde, bipyridine disaldehyde, bipyridine disaldehyde. These are all the some of the electrophiles we have used for our group research work for the first time. Similarly, these are all the activated alkene already known, but for my group, same compound having two acrylate activated group in the same compound. The reason you will see, if you see, take this acrylonitrile, you have only one double bond attached to this. This is activated alkene, one set. But if you compare this compound, you have the same molecule but having two different activated alkene in the same product. And in order to achieve whether simultaneously this Bayesian reaction would take place. That is the reason we were very much interested in this compound. And also you can see activated alkene attached to the propargyl group. Sometimes you can further modify propargyl. Sometimes we have seen when we use propargyl group, it will also easily getting eliminated. So those are unusual acrylate we have used. And a linear 10-member linear cycle, and also bridged cycle, pressure butanol, diallyl acrylate, and benzofuran attached compound. So we have used several unusual acrylates. So whatever I have listed, we have extensively used this one. And methyl acrylate and acrylonitrile are well known in the literature. All other are very rarely known. We have used it, and we can see it in the coming. The first work was started using simple benzaldehyde, because when I joined the Trivandrum, other than benzaldehyde, I don't have money to buy, and there was a language problem, there was a chemical availability problem, many problems were there. So when I joined Trivandrum, Dr. Raja Singh, now he is working as a professor and head at Surandai College near Tirunelveli, I think. And he was my first PhD student who wanted to work on this particular Bayesian reaction. So he took benzaldehyde, and he borrowed some methyl acrylate from the polymer chemistry department of NIST, and we have used triethylamine or DAP catalyst was available plenty. He has prepared this Bayesian product of benzaldehyde first. Then he converted this benzaldehyde using homopropargyl alcohol. Propargyl alcohol is 3-member system. Homopropargyl is 1, 2, 3, 4-member cyclic propargyl system. Simply by heating this, he derivatized Bayesian product to this one. And I did my PhD work on radical cyclization. If you have triple bond, if you add tributyl tin hydride, you will generate a vinyl radical. It will add to this double bond so that you will get cyclized product. So by this simple method, we have synthesized a 7-member oxygen ring. It's very rare, very difficult to synthesize. If you look at this molecule, 7-membered oxygen heterocycle having 4 substitution variances. Otherwise, if you were asked to write a retrosynthetic analysis for this compound, it's very difficult to synthesize. But we have achieved in 3 steps. Tetra-substituted oxygen ring formation was reported. And similarly, if you remove this hydrogen, so you can prepare tri-substituted or tetra-substituted, you brilliantly design your starting material so that you can prepare this particular model. So instead of 4-membered system, if you do 3-membered system, definitely you will achieve the corresponding 7-membered oxygen, 5-membered oxygen, and by differently adding propargyl group, same tributyl phenhydrate chemistry only, we was also able to synthesize 5-membered. So we published 7-membered ring in tetraethyl. This is in Simlet and this is in Chemlet, and all these 3 work were initially did with only benzaldehyde. He got his PhD with 7 papers or so, and we have some basic knowledge about Bailey-Simon chemistry of benzaldehyde. But the new strategy what I was using is introducing radical chemistry into the Bailey-Simon starting material in order to get 5, 6, and 7-member oxygen heterocycle. So this was we are familiarizing, and the first student also got PhD during 2007. And later, my screen is not moving. So he completed his PhD using benzaldehyde. And after when he was doing PhD on benzaldehyde Bailey-Simon reaction, I was reading an article in the NIST library. Before that, I just want to introduce a molecule called isatin. This is 6-membered fused with chiron with 2. Hello. Please ask some of the people who are using their mic should be off.
Dear participants, kindly switch off your mic.
Hello. Are you hearing?
Yes, sir.
Okay.
Yes, sir.
Okay. So, isatin is well-known molecule. I think we have studied in BSc chemistry during dye chemistry. Isatin is the monomer for the synthesis of indigo dye. If you dimerize isatin using air oxidation, it will get dimerized. So that is nothing but indigo. So isatin molecule is well-known. The structure of isatin molecule is given here. So why isatin molecule is attractive? If you are basically an organic chemist, by looking any molecule, you can see whether any functional group is present, so that you can synthetically modify and prepare the useful product from the simple molecule by chemical transformation, that is otherwise organic chemistry. If you take isatin, the 3 position is highly reactive, so you can plan of synthesizing n number of molecule at C3 position. And isatin has NH, free NH is there, so that you can do NH functionalization by alkylation, arylation, many chemistry can be done here also. And in the same molecule, you have aromatic system, so that you can think of any functionalization of aromatic ring system. So actually, if you see, the indigo dye was only functionalized at C3 position. Other 2% people never used it, but in our chemistry, we have extensively used it. You can see in the coming slide. So this is some background about the molecule isatin, and not only isatin. You can think of any molecule. Basically, if an organic chemist take the molecule, write the structure, and look at the structure with a lot of functional group. Apply your fundamental chemistry so that you can do any synthetic transformation into useful product, so that you will get papers published, and you can also achieve your PhD. So the story started during the year 2004. At that time, I was reading tetraethyl letters because I was familiarizing with the Bailey-Simon chemistry. So I was searching what are all the papers published across the world on isatin Bailey-Simon chemistry. At that time, I saw isatin has been used as an electrophile, and they used a few activated alkene in presence of base. So they got this adduct, and in that paper, the title is isatin as electrophile. That's all. So they reported around 6 to 8, 9 isatin molecule reported. Nobody was worried about this. This was published in 2002. The story started when I was studying 2004. So now you can see this why this particular molecule attracted me personally, because when I read it in 2004 or 2005, nobody was used that molecule. It's reported as an electrophile. That's all. But when I looked as a organic chemist, I saw this is highly functionalized group, and you can see a lot of diversity pattern is also there. NH pattern, aryl fashion, double bond, electron withdrawing group, tertiary alcohol, amide functional. You can see in single molecule you have n number of options for synthetic. So I call it as diverse reactivity pattern. And this molecule nobody was used for any synthetic transformation. So that was the advantages for me when I was reading this paper till 2005. And after I'm reading, I think December of 2005 or so, we have started using this particular starting material. Remember, this was not reported by us. This is reported by Gordon et al. From Brazil. Brazil is South American country. You can from that authors they reported this molecule as electrophile. So why actually it is interesting, you can see, if you see this structure, there are lots of natural products are listed here. All the products, you can see the isatin molecule as a core structure. So if you see this, if you see this particular molecule and this area, there are lots of natural product has isatin as the core structure. And if you look at very interestingly, all those reactivities are functionalized at C3 position of isatin. 1, 2, 3, wherever you can see C3 position is highly reactive, and many natural products are functionalized at C3 position only. So this is not only used spiroxindole, so spirosection, and these are all the drugs. There are many molecules are pharmaceuticals, and some are the intermediates for the alkaloid synthesis. Obviously, since nitrogen is there, it is antimicrobial, and it is also used as a biocide. So now this slide justifies why isatin is important because of these properties. We chose this molecule. So remember the previous slide, this molecule was reported initially, and this is the Morica Bailisman Adaka isatin reported in 2002. We prepared again after following the procedure in 2006, and after preparing the starting material, we took this compound, treated this with the HBr, hydrogen, instead of hydrochloric acid, we are using HBr in acetic acid medium. This double bond comes internally, and rearrangement takes place so that we are getting a bromide, highly reactive bromide. You can also convert this double bond to OMe also. So this highly functionalized group, if you do sodium borohydride reduction, simple methanol sodium borohydride of this one, you can get cyclopropane. So in organic chemistry, preparing cyclopropane is really difficult, but we have achieved. And that was the first work we did in 2006 tetrahedrine. At that time, we did not know how to write big journals, organic letter or JOC and all. At that time, very familiar journals were only tetrahedron and tetrahedron letters. I got it published, and later we also used the same indium, so that the indium bromide will form, and using formaldehyde we got a lactone, 5-membered spiral compound, 5-member pyrazole compound. We have done n number of synthetic transformations. Actually, each arrow is a paper. Each paper is a lecture of half an hour. I am just giving the list. If you see these many compounds of spiroxindole, C3 portion were prepared by our group, and initially in Trivandrum, these 3 people were working on this molecule. Dr. Vaidyanathan is the assistant professor now at the Government Arts College, Viluppuram, and she is Dr. Devi Viswambaran. She is associate professor in NIT Trichy, and he is Dr. Selvakumar working in Madurai and Tyagaraja College. So these people were initially worked on this synthetic transformation, Bailisman Adaka isatin. So later, during 2008, I moved from Trivandrum to Chennai. And initially, after moving, one girl from Madurai, CSR qualified student, she also worked on ISATing. But what she did was, she used a different activated alkene. This particular cyclic activated alkene she was using, maleimide, and substituted maleimide. She was able to prepare an array of compounds which are very difficult to prepare and very, very hardworking girl. She got publications in 2013, two organic letters in the same year, and the tetrahedral letters. And I'm just giving only few work on isatin, and many of our isatin work are Bayesian are not reported here. Only I'm reporting from each student. She was able to prepare all this pyro C3 question only. If you look at 3, all isatin at C3 functionalization was done. Of course, we derivatized the N also. That's not a matter, but C3 functionalization is very important. And this boy is working in Thoothukudi, and he was able to prepare C3 question with the conjugated triple bond. Hello. I request participant, please switch off your mic. And this triple bond, and in place of triple bond, the 3-member nitrogen aziridine were also prepared. So if you can see 3-member aziridine attached to a vinyl group. So this vinyl cyclopropane will undergo ring enlargement, VCP rearrangement, so that we are getting cyclopropane. Got this degree. And these are all other molecules. Some of the molecules we have reported from isatin. So later, his name is Dr. Peri Raja. Right now, he is in Coimbatore. Polytechnic College recently he has joined. His idea, from his research, we were able to prepare isatin-based colorful molecule. This is colorful molecule means fluorescent molecule. He was able to prepare pyro compound, linear compound, and 4-member acetidine compound. Several molecules he has been synthesized starting from isatin. This particular slide, we have not used Bayesian vanillite, but we directly used isatin as a starting material. This particular case, but all are fluorescent compound. So when we were working more on the isatin compound, we thought to increase the property whether this position is fluorine, and if we keep double bond here, this is fluorinone. This is the fluorinone. If you take fluorinone and do a lot of Ka2 chemistry and all, we were able to prepare a different colored compound, fluorescent colored compound. This was done by Dr. Meera. Now she is group leader at Syngene Biocon Bangalore. So some of the other fluorescent compound in collaboration with the Madras University, Dr. Arichandran was my contemporary during PhD, and we were doing some contemporary chemistry. And he was using salicylaldehydes and 3-component green catalyst system. We were able to prepare some kind of 4H fluorescent 4H chromin molecule, and this was published in Dyson Pigments 2017. One of this candidate, I don't know. She got her degree, what she is now doing, but this was a collaborative work published in a highly rated Dyson Pigment. And much more sensors and activators, again fluorescent molecules were synthesized from orthophenyldiamine. From this compound, it was prepared again 4 chromins and the chromophenazines, because chromophenazines are these 2 double bonds. So as I told you in my electrophiles, we were interested to use different electrophiles. We first used isatin, later we used the other compound. Now we wanted to introduce or explore new chemistry, so that we selected ferrocene. So aldehyde electrophile attached to the organometallic compound ferrocene. and we were able to prepare its corresponding Bayes-Simon adduct, one side mono adduct, and first time with if you take this ferrocin aldehate, you can get this adduct. This is the first time reported one part reaction to Bayes-Simon adduct. This adduct would be possible, and we also used mono preparation, one side unreacted, one side reacted, and using this molecule we were able to prepare a large number of ferrocin-based derivative, and she also got a very good paper published in Organic Letter. Interestingly, we managed this Asa-Bayes-Simon reaction very interestingly, and this work was published in this Organic Letter. I should be very, very happy that this is now in IISER Bhopal. Now able to publish last month, he called me, sir, I used the ferrocin chemistry. Now I have published a paper in Angron again. So I was very happy. I introduced the ferrocin chemistry to her, and independently now she is doing excellent work at the IISER Bhopal. She is a women scientist there. So we used ferrocin aldehate here. Now we want to switch over other electrophiles. The big problem, if you look at this molecule, is a bipyridine. Bipyridine is the chemistry we studied in the complex chemistry, where bipyridines are used as a ligand for the preparation of many complex metal complexes. So the problem of metal bipyridine is solubility. So bipyridine, if you take, it is very difficult to solubilize in any solvent. So preparing metal complex is very difficult. So we thought whether we can functionalize this kind of bipyridine molecule by introducing functional group so that its solubility will be increased. So what we did, we purchased a 4,4-days dimethyl bipyridine commercially available, and convert this molecule to aldehate. Selenium dioxide oxidation will give this, and the more tedious oxidation will give dialdehate. Now you have bipyridine monoaldehate, bipyridine dialdehate, and we have used a large number of activated alkene. We were able to convert insoluble, very difficult to soluble bipyridine into very easily soluble bipyridine derivative. All these compounds are soluble in CDCl3, and this will soluble only in DMSO. So we solved this problem. This boy also got his PhD from bipyridine chemistry. So she is my actually she was my MSc classmate, came as a part-time PhD, and she used pyridine as aldehydes as electrophile. Pyridine 2 aldehate, pyridine 3 aldehate, pyridine 4 aldehate, and she was able to use the first time this activated alkene, labile activated alkene, and lengthy aliphatic chain aldehate activated alkene, and tightly bridged isobornyl acrylate. These are all she was using for the first time, and she initially she also prepared Bayes-Simon isatin and propargyl alcohol, so that when we did the 3+2 cyclohexane reaction, 1, 2, 3, 4, 5-member ring, and when you ring open this, you can prepare this. She reported these two molecules. Particularly, if you see the B ring, 1, 2, 3, 4, all 4 persons were substituted. This chemistry was done in 3 steps. So Bayes-Simon substrate are very interesting substrate for any synthetic modification. You have to sit and use your fundamental chemistry, you can achieve interesting new molecules. So she is exactly of same my age, but she was able to convert work at the age of 48, 49. She could able to prepare these wonderful molecules, and that was published in 2017 in videos. Later, one collaborative work, one student from VIT Vellore, he came, is now actually Malini is a professor at a college in Karnataka, Suliyam, and this boy has completed his PhD. Right now, he is working in Calcutta in a private company, group leader. And this boy came from VIT to work with me for a while. And when he came, he said, "Sir, I have only anthralenamide. It is available. You can buy it anthralenamide 100 grams for 1,000 rupees or 1,500 rupees." And with that chemistry, what he can achieve? That was the big question. but by using our synthetic transformation knowledge and the fundamental chemistry, this boy was able to complete his work preparing all these kind of compound in 1.5 years. He did all this compound, 4 paper work in 1.5 years, 12 hours work per day, tremendously completed his work starting from amino amide, biphenyl derivative, 9-member diazonone derivative. You can see RCM product from all from this anthralamide one. So he is Dr. Mohanna. He worked in my laboratory for 2 years. And the latest PhD from my group is she got her PhD degree last month, I think. She was preparing propargyl alcohol. If you see this triple bond, single bond OH propargyl alcohol, when you have a propargyl alcohol attached to the fluorine, and when you add acid here, the acid will eliminate this OH group so that you are generating a carbocation. And to neutralize this double bond will come here so that you can also prepare its allynyl cation. So propargyl alcohol on treatment with Lewis acid, either it will generate propargyl cation or allynyl. So depending upon, you can quench this within a nucleophile. So she used the nitrogen nucleophile, she used the imine nucleophile, she used the nitrile oxide nucleophile to quench this active compound. So there is a big story about it, but the summary is when propargyl alcohol of fluorine were prepared, and either depending upon the reactivity, propargyl cation or allyl cation, she was able to prepare a variety of nitrogen heterocycle compounds. She also got published in NJC, letter and all. She got her degree. The chemistry is totally different. So far I am summarizing whatever I have done. In another few slides, I will jump into the today's topic. She is Smile about to complete her PhD. Her last chapter work is going on. And what she did was, when she was using DMSO and in allyl bromide, it generates a highly reactive DBMS, highly reactive compound. And when we treat this with secondary amine, she was able to, in one part, bromination takes place, allylation also takes place. We did not use the HBr is did not use unwasted, and we were able to use the byproduct HBr as a brominating agent and as well as allylating reagent. So we have developed a new reagent by mixing allyl bromide with DMS. So it gives allylation reaction as well as bromination reaction in one part. This particular chemistry is benzene chemistry. This I am going to show you later. And after that, the same propargyl chemistry, when she was using pyridine hydrazine, 2-hydrazine-pyridine compound, he was able to prepare a different variety of heterocyclic compound. This is also now available in online and SBS Omega in press. And I will summarize this work in a later case. And this has already been published. And she is now finalizing one more work to complete her work. So I think so far I have summarized or discussed whatever the chemistry we are discussing in our laboratory. And now the topic is how we are using benzene for all this chemistry as a benzene intermediate as one of the reactant in our chemistry. So coming to the MSc chemistry students, first of all, benzene is a reactive intermediate. So when you go for interview, they will ask what is reactive intermediate. You have to tell a reactive intermediate is a short-lived, highly energy and highly reactive molecule. So when you generate reactive intermediate, it will quickly convert into more stable molecule. So whenever you write reaction mechanism, you will write these are all the intermediate and how intermediate is converting to the product and all. We are teaching in the classroom or we are studying during our course. And in the exceptional case only, these compounds can be isolated. Intermediates are very, very difficult to isolate because it is highly reactive, it will undergo product formation. But for some cases, you can isolate reactive intermediates. What are all the conditions? If you store it at very low temperature or you can use the matrix isolation. So you can keep that intermediate in a matrix system so that that can be stable. And when the expression is indicator, the presence of intermediate is indicator, reactive intermediates can help explain how a chemical reaction takes place. So we are using reactive intermediate, introducing to the students to explain them how a starting material is converted to product, through what are all the steps involved in between. During reaction mechanism, we are clearly indicating or teaching what is the reactive intermediate. This is little bit background about reactivity or reactive intermediate in organic synthesis. So the moment when we are teaching reactive intermediate, we want to introduce students what are all the reactive intermediates known in the organic chemistry. I am listing here very few, very common cation reactive intermediates. Generally carbocation. So here big stories are coming: primary, secondary, tertiary, carbocation, classical carbocation, non-classical carbocation, stability. Many stories we are teaching here. Similarly, carbanion having a negative charge, radical, and carbon having two pair of electrons, nitrine, phosphanidine, and these are all aliphatic in nature. Most of the cases, these are all aliphatic. And there is one more reactive intermediate, which is benzene as triple bond, and that is called arene chemistry. Benzene. If you have another ring, generally we call it as arene. If the triple bond is in the benzene ring, so we call it as arene. So the benzene chemistry was initially started by Dr. Meera Krishna, who is now, I already introduced her. She is working in Bangalore as Syngene Biochem. And for that particular work, we want to give some information about benzene, the reactive intermediate, how benzenes can be generated. And in the school and all, you anthranilic acid, if you heat it with low temperature, -78, and if you use butyl lithium, very difficult to generate benzene. So now there are n number of methods are known in the literature. You can generate easily. During our MSc time and all, benzene generation was very difficult. Now for past 10 years, generation of benzene is very easy. Room temperature, stirring, you can generate benzene. I will show you how. And we will also give some information about natural product containing oxindole. So the benzene chemistry started in 1902, and first it was observed in 1902 by this reaction method. So when they have benzofuran, they treated with base and the ethanol, they observed a product like this. Nobody knows that what is the intermediate here. So this was first observed in the year 1902. Later, it was believed there is something, but the structure was not known. When years go on, after 40 years, this Wittig et al., they gave, if they take fluorobenzene and treated with butyl lithium and treated with benzene, they got this kind of product. So what could be the product? This dipole structure is possible, and they call this kind a dipole depiction of benzene. But this is also not true. This is also possible. And later, during 1953, Roberts, he only assigned what may be the structure, unusual structure, triple bond, and this is the electron cloud structure of benzene. And they have a lone pair of electron here, highly reactive, and this structure was proved by doing a carbon 14 labeling experiment, and there are reports are there. This is the structure, arene C triple bond C. So this is the actually reactive intermediate benzene chemistry started, how it was evolved. Now coming to the picture, how benzene nowadays can easily be prepared. So if you see, we have listed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, almost 12 types of methods of generating benzene. Different starting material, different reagent, you can generate benzene. But the latest one is using this TMS triplet of benzene, using cesium fluoride at room temperature, you will generate benzene, highly reactive benzene. And you can also think any other method, but the best method today available is this, the green one. And once you have a triple bond, benzene, one can immediately think organic chemistry of benzene. If you think this is a 2-pi system, treat with the 4-pi system, this will undergo Diels-Alder reaction. If you think 2 plus system, 2 pi, again 2 pi, 2 plus 2 cycloaddition. 2 pi system, 1,3 dipole, 1,3 dipolar cycloaddition. If you think it's a nucleophile, if it is Wapler dipole system, this will undergo multi-component reaction. This will also undergo insertion reaction. This will also undergo transition metal catalyzed reaction of substitution. So now if you see benzene, it is ready to undergo a variety of named reaction or reactions depending upon the reagent, giving rise to different structural products. Very interesting. So this I have already shown you, don't worry. And so we have started our first work again starting from this. So I just want to give you some background about benzene, how it is reacting in C-arylation reaction. I think benzene can also use the, see this is the benzene. If you react with, if you generate benzene, if you react with this particular compound, this person it is getting arylated. So depending upon the starting material you are using, benzene, as I listed in the previous slide, a variety of reaction it will undergo, giving rise to different products. So what is the first study we took? We were working on, you well aware that we were working on Bailey-Silman chemistry of isatin. This is the Bailey-Silman adduct of isatin. And we wanted to see if I prepare Bailey-Silman adduct, I have a double bond. I have a double bond, whether it will undergo 2 plus 2 cycloaddition reaction so that I will get a cyclobutane product. And I also thought shift this terminal double bond to internal double bond and again do 2 plus 2 cycloaddition so that you will get a spiro compound here, 4 member. Here you won't get a spiro, you will not get spiro but 4 member. So synthesis of cyclobutane derivative is not known with Bailey-Silman chemistry, particularly with isatin. So that is the reason actually why not I used benzene 2-pi system. Why not I use double bond of Bailey-Silman and 2-pi system so that whether I can get cyclobutane derivative. That was the original plan. So we purchased our starting material commercially available, and we thought initially she prepared Bailey-Silman adduct of isatin, and when she treated with benzene, very interestingly, she got starting material back. That was the product, no reaction occurred. And I thought no reaction occurred because if H is here, H will be quenched by this so that reverse reaction takes place so that isatin was formed. So to avoid hydrogen, we prepared this alcohol as protected alcohol. When again treated with benzene, she got again the starting. No reaction took place. We were expecting this product that was not formed at all. So initial reaction, first day reaction with benzene, second day reaction with benzene was failed. Then we thought, what happens if we are shifting this terminal double bond to internal double bond isomerization? You can see the very first slide. Trinitized orthoformate, K10 play, micro irradiation, we shifted this double bond to internal. And again, this double bond is available. This triple bond, benzene double bond is available. We thought whether it would react. So actually 2 plus 2 reaction should give cyclobutane here. But what we observed was 5-membered ring. Reaction took place luckily, and we got a new product, not the expected product. And in addition to the cyclic product, we also got the C-arylation product also. And that was very, very interesting. Bailey-Silman chemistry, first time we used benzene. So you can see the structure of cyclopentane was assigned based from the proton NMR, carbon 13 NMR. Particularly, this pyrocarbon was observed here at the 64 delta chemical shift value. Depth as well as high resolution mass spectral value are easily matching with assigned structure. the OpenScience C arraylation product was also assigned based on the spectroscopic data. So we were, in addition to the spectroscopic data, the structural proof was obtained from the single crystal. So 100% structural proof was obtained from crystal, particularly this propargyl compound, this C-arraylated product, this propargyl C-arraylated product were crystallized. So there was no doubt about the structure of the product. So after having synthesized the structural proof, we were optimizing this compound by using cesium fluoride or potassium fluoride. The fluoride is the source for generating the alkane, and we were also using equivalent of arine, duration of the reaction, temperature of the reaction, and all were used as a tool, so that we got this 5A and 6A, 5A and 6A in a better way. So other product, one acylated product were also obtained, and that compound were also proved by the spectroscopic data and also crystal data. So now you can see why I did not get 4-membered product, but why I got a 5-membered product. So this is our starting material. Source of benzene. If I use cesium fluoride, I generate this particular benzene, and Bailey-Simon adduct is this one. So if Bailey-Simon adduct directly adds here, you will get 4 members. But since it is undergoing conjugation and the quenching takes place from the third position, so we were able to get only the 5-member ring. In this position, if it is quenched by hydrogen, instead of cyclizing here, the C arraylation product also formed. So we have clearly explained the mechanism of this reaction. Why we are getting a C arraylation product and also 5-membered product, Spiro 5-membered product, not the 4-membered. So here also we used benzene for Bailey-Simon adduct did not work. Maleimide adduct benzene addition did not work. Only adduct with isatin only the benzene chemistry worked. And this chemistry also did not work for benzene, kerosene derivative, maleimide derivative, benzaldehyde derivative. It did not work. Only we observed that this is the most suitable double bond compound available for the PA reaction. But we have choice of preparing a lot of arrays. See, this is simple benzene. You can buy bromobenzene. You can precursor for bromobenzene, 1-naphthyne, 2-naphthyne, and heterocycle benzene can also be prepared. You can buy it a source precursor. You can buy. You can generate in the laboratory. Pyridine, 2-pyridine, 3-pyridine, and this is indolent. So that if you take indoline, if you add here, your product is different. This is different product. This will be different product. So each benzene will react in the same pattern but gives different structural product. So these are all the compounds he was able to prepare, say, from benzene, variety of compound. And interestingly, you can see lots of example. We were reporting CR-related as well as the Spiro compound. This is the 1-naphthyne. This is the 2-naphthyne product. Yes, he was able to prepare. This is indolent product. So variety is there. You can see indolent, 2-naphthyne, 1-naphthyne. Totally structures are different. So these are all. This table gives the yield of these two products. And the product which we got can also be easily further synthetic transformation by Click reaction, since alkane functional group is there, treated with the sodium azide, benzyl bromide, a Click product was obtained. And this terminal alkane, again other molecule can also be coupled. That is one Eglinton coupling using copper catalyst. 1,3 alkane system were also prepared. And she completed her buswork using benzene by doing all this reaction. And structure of this compound, the triazole and 1,3-diene system were confirmed. Her first work was over, simple. Balisingman adductor pistatin, its isomerase reaction using a variety of benzene. He was able to prepare Spiro 5-member ring and also C-related product. And further synthetic transformation was done by triazole synthesis and also 1,3-diene system. We completed, our group first time we completed a benzene work. So if you scan in India, you can see only very few groups are working on benzene because they don't want to take any pain, any fast reactive starting material they don't want. But I think I took it as a challenge at that time, and still even today we are trying to use benzene in our game because by structure it looks simple, but by application you see it has lot of application in the material chemistry, dye chemistry, electrochromic materials, semiconducting material. Lot of applications are there if you are having a diphenylamine or triphenylamine. Basic information. And if you see literature, so these are all the triphenylamine based molecule used as a material. Enzyme chemistry, and you can functionalize diphenylamine or triphenylamine. That was the idea. But imagine that we are going to introduce for functionalizing this molecule using benzene chemistry. So what is the idea? So Novana was using anthralenamide for his chemistry. I showed you one slide. That material was left over in our laboratory. And the benzene was used by us because this is the starting material, cesium chloride. If I add, I will get this alkane. So the idea now is what will happen if I have triple bond here and nitrogen here, nitrogen. Whether nitrogen adds here, so that I am getting the macrocycle. That was my dream actually. What will happen was surprising. You will see next slide. So the idea was preparing this molecule by directly adding alkyne one end here, other end here. So anthralenamide, benzene generated, added in situ, and we left. Instead of getting cycloaddition product, we got N-arylation product. That means this benzene added replaced one of the hydrogen here, monoarylated product. And the second hydrogen also replaced. This was prepared in 82% oral weight, 3A and 4A in 8:2 ratio. So this reaction was not occurred, only N-arylation was the product. What is interesting in this, if you see, you can now think of a diphenylamine here. You can also think you can keep a triphenylamine product, but by this method, the diphenyl or triphenylamine, we introduced an amide group here, orthoposin. Introducing diphenylamine or triphenylamine, functionalization at para is easy. Functionalization at para is easy, but you cannot selectively functionalize the diphenylamine and triphenylamine into the 2%, orthoposin of that triphenylamine. So that was achieved very easily by this method. You may ask question, only you have functionalized at C3%, orthoposin? No, we have functionalized meta, we have also functionalized para. You will see how we did it in a coming slide. So structure of this orthoamido diphenylamine were proved, and the triphenylamine orthoamide also proved, and this triphenylamine compound was crystal, no doubt about the product structure. And we were also interested to optimize this reaction. So if you use cesium fluoride, you can use different solvent. You can also use potassium fluoride 18 crown meter to trap the potassium so that fluorine ion will come. And equivalent of that, we got the maximum yield. So source of fluoride, cesium fluoride or potassium fluoride you can use. And to release fluorine, you have to use potassium fluoride plus 18 crown meter. This is little costlier method, and this is the easy method. So what is the mechanism? If you take anthralenamide, benzene you have generated from this fluorine benzene generated. This lone para electron is nucleophilic attack, then it is quenched with hydrogen, so that initially are getting biphenyl amine. And the second product was also getting from mono product, so you are getting this product. Reaction mechanism is straightforward. That is not a big deal. But the interesting point came, we have already in our fridge, these are all the precursor available. Benzene, bromobenzene, methoxybenzene, and this is metamethoxybenzene and indolone. And instead of having anthralenamide, we also prepared iodoanthralenamide. And commercially, you can prepare meta-anthralenamide. Commercially, you can also prepare para-anthralenamide. And you can also introduce, instead of benzoylamide, you can use heterocyclic amine, thiophenylamine, benzopyranamide, pyridinamide, and also instead of amide, you can use also sulfonamide. So when you have these kind of options, think about crossing. Take this, react with all these things, take this, react with all these things, take this, react with all these things, so that you are getting variety of products. So in this manner, when I was using orthophenylamine, orthoamido compound, I got meta product, ortho product. If I use meta product, if I use para product, and I have a lot of choices, I can introduce the diphenyl system and the heterocycle also. So by using simple trick, I was able to find indoline also. One indoline, other side aryl system. So triphenylamines with different substitution, different positions were achieved by simple reaction. Okay, select the starting material, select your benzene, get this product. So we have done a lot of synthetic transformation after preparing this molecule. This molecule was treated with biphenyl benzaldehyde, so that it was derivatized with aldehyde. It can be cyclized here, and the derivatization was done. This kind of this derivatization was also prepared, and we have done a lot of synthetic transformation using when you have iodine here substituted here, you can think of a Suzuki coupling with a boronic acid. So she was able to prepare this molecule. We have also converted this molecule into again bipyridine molecule. Lengthy bipyridine molecule are also synthesized. Simple chemistry only. Just take Suzuki product, treat with aldehyde. The aldehyde reacts with this one, so that you are getting this product. If you use two equivalent, again you are getting other side also, you will get the product. So structure of that aldehyde derivative, you can see a presence of aldehyde here. And the lengthy product were also cyclized product were also obtained. Masses and all correctly matching. And after having synthesized this molecule, we were establishing its photophysical property. Its absorption was measured in 391, and this triphenylamine molecule emission was measured at 462. And its derivatives were synthesized, and this showed three different absorption. And exciting this, it is a blue emissive molecule rest are also prepared, almost similar to this. And after preparing this molecule, we were examining its photochromic property, hexane, dichloromethyl, increasing solvatochromic, increasing out of the polarity, whether the absorption changes, and we have observed 535, not much change, but in particular DMS species, we got the reduction, and the hexane was found as a very good solvent for this case. These are all the absorption spectrum. This is corresponding to the emission spectrum. So in this case, we have evaluated the photophysical properties of all these molecules, and this is the data of those molecules, absorption emission of each molecule, and this is the tabular column of those molecules. Interestingly, the quantum yield of this product was very high compared to other fluorescent molecules which we have reported earlier. So second portion also we finalized, and that work was published in New Journal of Chemistry. Right, we can see this was published in 2019. Now coming to CAD portion. Next, benzene work. this work was published in 2020. Each year she was completing one paper, one work on benzene. And let me introduce something called azomethane halide is different. Azomethane imine. So C double bond N is imine, and it is conjugated with nitrogen. This is called iminium imide. And if you have diazo compound, it is diazinium halide. And we were interested to use azomethane imine. So I will introduce that. What is azomethane halide? It's a highly reactive intermediate, which reactive intermediate I have not. In fact, I have shown you some previous slide, but azomethane imine, azomethane halide are also reactive intermediates. So now, if you see characteristics of azomethane imine, you have two types of azomethane imine, azomethane imine. So this is the structure. These two are the example of open chain, and you can also prepare cyclic azomethane imine. So depending upon starting material, you have azomethane imine can be classified to acyclic and cyclic. And once you generate this reactive intermediate, you react with this dipolarophile. So this will also undergo dipolar cycloadation, 3+2 cycloadation, higher order cycloadation, arylation, alkylation, asymmetric synthesis. These azomethane halide easily undergo this kind of reaction in order to get a diverse dinitrogenated heterocyclic compound. This is the fundamental basic about this. So now how we are calling NH2 is hydrazine. NH2 attached to double bond is diazoalkenes, and this diazoalkene, when it is substituted, azo compounds. These are all azo compounds. These are all a nomenclature of nitrogen based compounds. So what was our study? You may ask the question. So when we took hydrazine hydrate and methyl acrylate, we can generate this particular compound, which is not stable, pyrazolene 3,1. And we have plenty of isotene in our group. So when we reacted with these two things, we were able to prepare a cyclic azomethane imine like this. This is also a reactive intermediate. Interestingly, but this compound is very stable. You can prepare and store it. And instead of methyl acrylate, if you are using methyl protonate, you will get the same cyclic azomethane halide, but a substitution here will be that this methyl will come here. So these two azomethane imine were reported earlier in the Organic Letter 2017, and it is very stable molecule. So following this, my student prepared these two azomethane imine, and we were interested to see what will happen if we generate a dipole here, azomethane dipole, and add benzene. So it is unknown. Nobody was using azomethane reaction with benzene. So we prepared these two starting materials, and actually we were able to react with benzene using this isotene starting material. So now the question is clear. You have azomethane imine, you have same azomethane imine, but additional methyl group is here. So precursor TMS triplet, fluoride source, generate benzene, you prepare your dipole, see whether your dipole and this diphase 2-pi system, whether it will undergo 3+2 cycloaddition, so that what kind of product is forming, and whether you can synthetically transfer that product was the objective. So she prepared this compound and we generated benzene, and then we added here, interestingly, instead of cycloaddition reaction, she got the C-arylated product. So this is pyrazolene, C-arylated product. This is a quaternary system, carbon. And the structure of product was clearly assigned by spectroscopic method. And this compound is also a crystal structure, no problem. Interestingly, optimization of this product was also observed. Very interestingly, when you have methyl group here, when you have methyl group is not there, you get pyrazole. But when you introduce methyl group, the geometry is changing, so that the product formed is not the open chain product, but a cyclized product. Same one. If you remove methyl, you will get walking chain. Introduce methyl, you will get cyclized, spirocyclized product. So these there are two isomers. One isomer is here, methyl, and the other isomer is changing here. This diastereomeric mixture were separated, and both the compounds were characterized. Both the compounds were different, column separable, characterized. And each compound, the structural was crystallized so that the geometry was drawn based on the crystal structure, relative stereochemistry. And optimization of best yield was also achieved by changing the fluoride source, reaction time, temperature, and all. We optimized this compound also. And we wrote a simple mechanism. When it is dipole, this undergoes using cesium. This dipole has a structure here, so that when you add benzene here, coming back to this undergoes very easy C arylation, and it is not fungible. Similar manner, it undergoes here, but when methyl is there, directly it undergoes 3+2 cycloaddition. So you are getting this product. Here, 3+ cycloaddition is not taking a C arylation. This is 3+2 cycloaddition product. So we have tested a large number of isotene-based azomethanamine, and we have stock of a variety of benzene. So later she purchased dimethoxybenzene, monomethoxybenzene, bromobenzene, naphthyne, and indoline. So we were able to prepare a variety of different benzene added azomethanamine derivatives, nitrogen rich. And this open chain compound again was propargylated with this OH giving propargyl group. And this propargyl again was trying to convert its triazole, and this free C triple bond C was converted to 1,3 alkane system. So structural proof was obtained from the spectroscopic data. And we have written a mechanism how benzene reacts with this, so that that portion of those work was also very, very interesting. So we prepared azomethanamine, reacted with a variety of benzene in order to get a lot of C arylated as well as pyroannulated. This happened. And the latest work was again with benzene. She is about to submit finalizing her work, and this work was very interesting. So in our lab, when I looked our, I will directly go to this. So we have this N, isotene N, NHSO2 M, this sulfonyl amide. So what happens if I am using benzene across this? Whether benzene breaks this, or benzene adds N arylation, or benzene undergoes cycloaddition. So since this starting material has lots of starting material, lots of reactive center, we want to explore this molecule. It was very, very interesting reaction. So this compound is commercially available. You can buy it from Aldrich, and we generated, when we added, we got sulfone, very interesting, diphenyl sulfone, and spiropyrazole, and also N-related product. That means this acted as a cleaving agent. Benzene acted as a 3+2 cycloaddition. Benzene also acted as a N-arylation in one-part reaction. We isolated all these products: arylation, 3+2 cycloaddition, and the cleavage reaction. All three reactions, benzene, we find for the first time it reacts with the same molecule, giving three different products. So when we were trying to control the reaction, whether I want this selectively, this selectively, this selectively, was not possible, because this reaction finishes in 5 to 10 minutes. The moment when you generate, products are forming immediately. So we were unable to control the reaction by preparing one particular molecule, but we were able to prepare all these products. So structure of sulfone, structure of pyrazole, pyropyrazole, and N-related product, crystal. So this is also crystal sulfone, and this also crystal. This one crystal was assigned. So we optimized the condition at 60 degree. Within 10 minutes, we were able to complete this reaction almost in quantitative way. So what are all the mechanisms for initially? If you start with benzene, if it is undergoing lone pair of electron here, you will get directly N-related product. If benzene adds with sulfur, it generates sulfur anion, and coming back, if it opens, you will get sulfone as the product. So when it is sulfone, the other byproduct is diazo compound. This diazo compound again undergoes reaction to benzene 3 + 2 minus, so that you are getting pyrazole. Pyrazole mechanism is known, sulfone mechanism is known, NRL mechanism is known. Starting from this one, from benzene as the reactive partner. So we have this time we purchased more benzenes precursors, and we used a lot of unsubstituted sulfonyl compound, and a variety of compounds are simple. These are all the sulfones, and these are all the pyrazoles, diazo compound, and these are all the NR-related compounds were synthesized. And most of the compounds were crystal. All the structures were assigned based on the crystal structure. We have structural proof 100%. So if you come, there are few more work is now currently being investigated using benzene, using our starting material only, satin, kerosene, fluorine, many starting material, whatever we have in our laboratory, and the benzene precursor, we are trying to get a large number of benzene chemistry. So I think if you can see now, if you take triphenylamines can also be synthesized, and the spirofluorinone can also be synthesized using benzene. This kind of diphenylamine, triphenylamine substitute amido group can also be synthesized, pyrosols. So we have achieved a large number of benzene chemistry products, and very tough intermediate, but very reactive. Structural proof is interesting, reaction mechanism is interesting. So we are exploring the benzene chemistry. I think here it is time for me to stop now, almost 3:30. The lecture should stop at least maximum 1.5 hours. 2 hours is too much. And let me stop here. If any question is there from the audience, you are most welcome. And I should thank Meera. She was the main person doing benzene chemistry initially. And the Smile is also did 2 reaction on 2 paper on this. Harichandran and my colleagues at the VAT, and funding from SEF, and a large number of PhD, MSc, MPhil students are contributing for me to speak with you all this big chemistry initially on satin, later on benzene. And those who have not seen, this is CLRI Chennai. All the work were done in this laboratory. So my laboratory is here. Right now I am sitting here. Inside I am speaking. This is our sitting room. This is our laboratory. So this is back entrance of CLRI. So again, this is the lab. You can see. I showed you this angle. Now you can see this is the laboratory, and here we are sitting in this inside. This is way to CLRI quarters. Winter time, summer time, you cannot see this kind of photograph. It will be all dry. And this is the latest research group, my collaborator from UAT, and Smile did one benzene reaction. Latest group, some students from UAT is also shown here. And I stop here, thanking you for listening this afternoon lecture after lunch. I know it was difficult for you to follow hardcore organic chemistry, but I was able to convince you some kind of interesting reactivity of benzene and some certain. Thank you, one and all. Bye.
Thank you, sir. Thank you for your very informative talk and on your research area on Baylis-Hillman and RN chemistry for the synthesis of various heterocycles. Now the floor is open for discussion. Participants, if you have any questions, any clarifications, you can ask our chief guest. Sir, I have one doubt regarding your Baylis-Hillman starting material.
Yes.
Is that starting material is stable? We have to store it in any special condition, otherwise then
90% of compound is stable. Baylis-Hillman you can store once together, no problem.
okay. Especially the ferrozine that Baylis-Hillman derived from.
Stable.
Oh.
Preparation is difficult, but ferrocene monoaldehyde and bisaldehyde usually we are not storing it for a long time. But ferrocene case you have to store in the fridge. But it will stable for months. No problem.
Okay, thank you. Participants, if you have any doubts, you can ask Professor. He is waiting to answer you.
You can also type question. You are unable
you can
to
send
ask
message.
You can type message in the screen.
So if any other no other question, we come to the end of the session. I request Dr. Balakrishnan, Professor Chemistry, Head Administration, to give the vote of thanks.
Very good evening to all. Good evening, sir. It's very immense pleasure to propose the vote of thanks. On behalf of Mohammed Sadak Management Principal staff, I would like to thank today's resource person, Dr. Sanmugam sir, Chief Scientist, Organic and Bio Devices, for this wonderful session. It's really very useful for us. And you mentioned students, all people now in good positions. It's very great to hear, sir. That's only the asset for our teaching community. It's very great, sir. Thank you, sir. And I express thanks to all participants from various educational institutions and research organizations for their continuous patience. I extend my sincere thanks to all my department faculty members for their endless support. Once again, I thank you all. Thank you, sir.
Thank you. You can also post mail, email
Thank you,
to any doubt if you have. No problem. Thank you.
Sure, sir. Thank you.
Thank you.